Hello. So we have to start. All right, so I'll switch to this one. Hi again. My name is Dmitry Chuyko. I will be talking about JVM on ARM hardware, particularly about OpenJDK hotspot. All right. So why I'm talking about it? Because we in our company do this stuff. So we contribute a lot to ARM support. And we actually release our own JDK binaries, not just for ARM, also for x86, don't worry. The product is called Liberica JDK. It's one of OpenJDK downstream distributions. And it's TCK verified, so you can just get it and try it and see how it works. That's the way how you can get latest security update to your JDK for free. Yeah, we're among top contributors, particularly active in ARM space, so you'll see what we do. I will talk about it right now. So what about ARM? Like, you came here today probably considering, interesting ARM. I know what ARM is. What's about Java? Probably it's so simple. Maybe I have my own production, my daily job. Then I program maybe in Java or Kotlin or something. Well, how it's related to ARM that I know? Yeah, ARM that we know is a company that makes great hardware that is not x86. In fact, really, there are differences. And yeah, the story is pretty simple, except the number of devices available in the world. That is a huge amount of devices. You see the number, like 30 billion, a lot of ARM stuff. And they are everywhere. Then you pick your phone out of your pocket. You see there's ARM inside. Probably in this laptop, Intel is not the only chip here. So there are some ARC chips and ARM chips, I believe, also. And of course, we expect much more ARM hardware in the nearest future. Like cars with a lot of sensors connected, they're using 5G to the net, and all of this working in real time. Maybe a lot of them will be ARM-based. For now, a lot of sensors pass their data using gateways, for example, to the cloud or to some other spots. And it's not so uncommon to see Java in a gateway. For example, you can again see the Liberica JDK in many products. A lot of gateways are capable to run Java. It is harder to imagine which ones are not. So a long, long time ago, it all started with attempts to bring ARM cores of that time to server instances. There was a company named Calxeda that made exactly that. They put a lot of ARM cores into a server board and tried to, well, get benefits out of it. It was not so good at that time, but things changed, and we'll look how they changed. So basically, then we talk about ARM hardware. We talk about quite different things available there. Most probably, you know Cortex designs, Cortex cores, and even designs made by ARM are targeted to different things. Then we talk about, well, generic workloads, what we work with, Java C, things like that. Of course, we talk about A things, like processors targeted to run applications, not just to do some tiny piece of work, but to do some interesting business logic. And you probably heard about some of this, like A53 A57. Who tried something like Raspberry Pi and, I don't know, any other single board computers? No? Yeah, of course, everyone. Everyone. By the way, like yesterday or day before yesterday, they released new board, Pi4, and it has not A53, but it has like A72 or something. So very powerful core. And ARM also allows you to do some interesting things, like to combine different cores in a single computer. Very different cores. So some cores may be targeted for better performance, some may be targeted for saving your power, saving your battery. And Intel also does this. Like this year, they announced that they will combine different kinds of cores in a single chip. So you see, in many things, hardware companies, they look similar. So yeah, I mentioned Raspberry Pis, and there are other single board computers, or just boards that are available to you, to consumer market, that you can buy and build your product around it. And of course, there are libraries, tools, all that things. Yeah, it's so simple. But let's get back to Java. It's very interesting that you can look at open ARM port only, well, starting from JDK 9. Anyone noticed? Really? So there was like closed port made by Oracle that has been open sourced. And by the way, first company that released JDK 9 for Raspberry Pi was, you know, what company? Yeah, Bellsoft. And that port supports a lot of JDK 9 features, of course, and we can run JavaFX on such devices in a very effective way, like using hardware acceleration, directly using frame buffer. It's very cool. It's so easy to take a small device and build a nice product around it using Java. And you can say, well, I'll use Go, or I'll use other, like some native runtime. Yeah, you can do it. But if you look at Java minimal VM, it will still provide you a lot of Java features, like security manager or, well, garbage collection. But in about the same footprint as, for example, Go, bundled with no libraries for Hello World. And if you bundle additional libraries, your footprint grows. So it's the same thing. And then we run on the device. What runtime expects to see there? Well, we don't know. So as on any other computer, then Java runs on something ARM. It detects CPU features, try to use best of them to be more efficient, like, for example, crypto extensions or checksum extensions, vectorization, not vectorization, but again, vector extensions. So you see, here on this slide, there's a bunch of extensions related to ARM v8, which is a new version of the architecture, which developed for many years. And what is not on this slide, like this year, ARM announced two interesting extensions, the SV2, so next portion of vector stuff, and also transactional memory. SV2 probably will come sooner, I don't know, because we are waiting for SV, which is an interesting thing because, you know, Intel has AVX, different versions of AVX, that simplifies a lot of calculations. So ARM made their own way to this thing. So they made a vector extension that doesn't have length. So you just write your algorithm, and then depending on hardware, exactly the same machine code executes in a different ways. So if machine has long vectors, it will use that. If it has shorter vectors, then, well, it will process data by shorter chunks. And when we talk about ARM, but ARM is a company and an instruction set. Here we have dual understanding of things. And there are licenses that actually produce hardware vendors. A lot of them. Even not all vendors you know are listed here. Like you probably, of course, know all the companies listed. But there are much more of them. And ARM announced a roadmap for server market or for cloud. Then the plan is to eagerly eat market share and also to show performance growth. Like it is already announced that this first step between Cosmos and RS is not 30%, but like 60% in some benchmarks. So that's a huge step. And even this first generation that's available today is very powerful. We'll talk about this. Few examples of what you can see in ARM server. For example, this processor made by Ampere. It is a nice replacement for, well, middle-class server instances, x86 ones, which works out of the box. So it was a long way to bring ARM servers to server commodity market, and it happened. So now consumers just buy them, install them in racks, and they work. And for quite normal price, you can get a powerful thing that has 32 cores, a lot of memory, and it's fast. In the same way, you probably heard that ARM instances are power efficient, and this is true in this case. Another example, KVM Thunder X2. In a two-socket machine, you can have up to 256 hardware threads available to you, virtual cores. 4 terabytes of memory, InfiniBand. And does it sound like fantastic? Do you think it's real? Yeah, it is. You can actually touch it. They exist, and you can buy one. That's how it looks. Again, 256 threads in a single instance, like this. I don't know if you see, on this slide, it's like 224 cores. You may ask why? Well, because too many cores for a single slide. All right. So we saw that there are a lot of vendors that make hardware. What about software? There are a lot of software vendors in the world. What would you expect from Java software? Have you heard about write once, run anywhere? Right? Yeah, we all heard about this. So we expect exactly this behavior, except some unsafe things or some bugs related to interoperation with operating system or hardware or byte endianness. You know, we have byte endianness. And yeah. So if you are not sure about if your favorite library or system if it works on ARM, you can just go to works on ARM.com and check it. Like if you put the Berica JDK there, you will see that it works on ARM. It's very simple. You probably see a lot of familiar logos here, right? What's your typical application? How do you deploy it? So does anyone create jars, like fat jars, Spring Boot? No? And then what you do, throw them in trash? No? Put in a container? Yeah? OK. How do you think? Is it hard to develop and to build a pipeline where you deploy something in a container and use it on ARM server? Yeah, it's not so hard, because you can even cross-build your containers from your x86 machines for ARM. That was a nice effort made by ARM, by Docker, and also by Amazon. And an interesting outcome here is that using that results, people implemented support for RISC-V for doing exactly the same thing. So Docker is now a cross-platform thing. It's very interesting. Getting back to OpenJDK ARM points. As I said, of course, then you implement specific logic for a certain CPU inside hotspot. You expect as a result that what you get is Java. So you check it. And of course, then we say that ports are there and they are production ready. They are production ready. But there are two ports. First one I already mentioned is a generic ARM port available in Java 9, 10, not sure, maybe also 11. But it has been deprecated and it was removed for 64-bit ARM machines. So it's not only active for ARM32. And by the way, Bellsoft is like a major contributor there now. And also, there's a second port, initially implemented by Red Hat, tended to support ARM servers. So it's called AR64. That's named of the architecture, some the official one. Oh, I haven't corrected this slide. You see, here's the list of garbage collectors supported, and ZGC is also supported now. So it's been integrated, and in JDK 13, it will be available to you on ARM. And a lot of features, like AppCDS, native memory tracking, ahead-of-time compilation, flight recorder. We participated in some of that, by the way. So let's get to performance. Then we talk about particular instruction sets. Many compilers, native ones, use a special thing called intrinsic to provide you better performance. So how does it happen? This special implementation replaces your function that does something by a very efficient assembly-written implementation using the most powerful things in a certain platform. Static compilers do that, and also dynamic compilers in Hotspot also do that. So how's about Java code? Can we speed up Java code with such intrinsics? How do you think? Yeah. So consider this interesting and very useful function. It sounds maybe unfamiliar to you, but it's really important and common operation. Then you just multiply two numbers and use a part of a production of the extended number. So this function is available to us since like JDK 9, for example. And if we let Hotspot to compile it with C2 compiler, we'll get a nice result. We'll have 14 instructions, each taking 1 cycle. Not bad. Probably even pipeline somehow. But can we do it better? How do you think? Yeah, of course, because I'm talking about this. Yeah. We can make a special hole to drill a hole where we can call implementation using JNI. How do you think? Is it good? No. That's because JNI is too expensive for this small piece of code. We can try to go from compiler's high level and to implement some IR or to optimize the IR already generated. But this solution, it's quite complex and maybe not so stable. From the other hand, there is already made solutions made for us by architecture vendor. A small H instruction that does exactly that according to specification. So we'll just go through all steps necessary to add in the intrinsic and add this. For a new port, it sometimes requires some utility steps, like fixing or adding support for certain instructions, the instruction of the instruction set, to a macro assembler, to the place that defines how we can use our CPU. And then we'll define a substitution piece of code using that macro instructions and a special node available to compiler that will be used as a replacement for some function, for example. But then we do all this. We need to make sure that we don't make it worse, that we make it better. So we have to measure performance. That's the favorite part. Let's imagine a dummy benchmark that just does some backoff and then does our target operation and tries to measure it. And it turned out that using this intrinsic, using a single instruction, the latency, what it was, 4, right? Instead of 14 instructions, with each with latency 1. We got exactly the expected boost, like 3.5x. Very good, especially in our world. But what can we do for enterprise applications? What your typical application does? Like my applications always read some inputs, write outputs, JSONs. Have you heard about them? Yeah. Generic application works with strings a lot. Also arrays. Just puts chunks of memory from one place to another and back, and And we know that since Java 9 strings became very interesting, because they may be latent strings and non-latent strings. And knowing that string is latent actually will allow us to save footprint and sometimes to see better performance. But what we need here is a special support with a lot of intrinsics working the strings. We again go to intrinsics here. And this is a platform-specific part of this feature. So yeah, it is nice. The feature will work even without any assembler implementation. But will it be efficient? How do you think? We need to measure. So when we measure, we need some special knowledge about what strings are typical. So I would say in your application, typical string is like 8 characters, believe me. This is a very important case. Well, this can be said in a different way. If your strings are mostly 8 characters, you're lucky because you're just like others, and things are optimized for you. So what do we start with? Then we use string constructor. And in case, then we work with compact strings in string constructor, which takes an array. We have to check, do we have some interesting characters in this array or not? So which string to construct, which encoder put on this string. And this all comes to a function that's called has negatives. That's an important intrinsic, then we construct a string. And you see, it has been annotated as a possible intrinsic. But Java implementation is fairly simple, right? We just go through this array, compare all bytes with 0, checking for negatives, right? The name is quite expressive. So what do we do in a processor when we go over some array? We load data. And in ARM, there are different ways of loading your data into the processor. Different instructions. You can load a single byte, 2 bytes, 4 bytes. You can also load data into special vector unit. I won't mention it here because all other logic operates with some general purpose things, and moving things between vector unit and general purpose registers, for example, it takes about like 6 clocks in some hardware, which is really expensive because they are not on the same die. So if your task is to load data, what instruction would you use of the instructions listed here? So like you have an option to load it byte by byte and to spend 4 cycles for each byte. I have an option to load a pair of white registers using just 5 cycles. One by one? No, yeah. OK, but there's a small problem. Then you use just white loads. You will go over your owned pages, and you'll get segfault. You can narrow loads, then you go close to your memory boundary, but you can be smarter. You can overlap your loads and use less loads for the same purpose. And there is a special way to ignore overlapped part using test instruction. And that's how this intrinsic may be implemented using this approach. But that's not all the truth. Because I said, yeah, it costs you something to load, but that's a cost of loading from L1 cache. Then you load from memory, you have different problems. Well, first of all, you load from memory, and this is very expensive. Not only like from some other caches, but then you go to memory, it's too long. But it becomes even worse than you load from unaligned addresses from memory. If you do it all the time, like you start from an unaligned address and then go by, for example, 16 or something, you will constantly get penalty for unaligned loads on different hardware. You can even see it in your Java program. If you will start something from an unaligned address on some hardware, even sometimes x86, it won't cost you the same. So how to solve this problem? Well, you must do some alignment before your main logic. But all that things really work well when you have a lot of data. Because, you see, the logic is very complex. So overall, all the tricks, they take a lot of cycles, a lot of instructions to implement. So 20 instructions is a lot. It's much more than a single cache line, for example. So the solution is to split cases. In simple case, you can perform simple check using less instructions. And in complex case, you may go to a very optimized version of your intrinsic, which may be generated inside your virtual machine as a so-called stub, which is also a more or less standard way of doing things. So stub also can be written in microassembler. It's just not dynamically generated, but statically generated, and your virtual machine, for example, starts. And all that logic, maybe that I described, may be expressed with instructions from ARM instruction set and written like this. But that's not all the truth. Because, for example, in this laptop, there are two hardware prefetchers that say, aha, this guy is loading some long array. We'll help him, so we make some data available ahead of time from addresses that are not touched yet. Some ARM hardware has hardware prefetchers, some doesn't. So you may really help it by using software prefetching, giving processor a hint that I'm going to read that memory soon. But you need to choose between the gain you have and trade-offs. Like you have additional instruction, and you also have to carefully choose prefetching distance, because otherwise it just won't be effective. So, then you're smart and you implemented all this, you get the final result. Speed up. So it's like up to 5x using all the tricks. Nothing made worse, but some cases made really, really fast. And it all depends on the length of the string. That's just one example. We made multiple optimizations, many of them. And jointly with a company named Kevium, we made Java enhancement proposal, which was delivered in JDK 9 while the work still continues. So it's JAP 3.15, and if you look there, you'll see description, how it's done. Most important categories of stuff implemented here. String and array operations, very, very important. Mathematics, you see it. This is a tricky part, because performance of some algorithm really depends on what hardware you're on. So you have to choose sometimes algorithm parts based on hardware. But what's for real benchmarks? Yeah, for big ones. Let's look at some benchmarks we know very well. Like enterprise application does something in warehouses. And to compare, we just took Xeon Gold, quite powerful one, and Kevium ThunderX. And you see that ARM server outperforms this powerful machine, both in critical and max JOPS. You see, settings are very basic. They're just a set of flags that makes some sense to limit your heap, to make it, well, work on a big machine, you know. And at the same time, the difference in price between those machines is like 2x. So the ARM one is like 2x cheaper. I don't see people running to the store. Because shut up and take my money. Yeah, I want this machine. And if you look at another benchmark, for example, we see exactly the same result, with some exceptions. Like this ARM server doesn't have, for example, vector extensions. And Xeon, of course, has it. So in some mathematical benchmarks, this is critically important and gives you very big difference. So But then they work the strings and things like this. Well, looks obvious. So you saw me touching the machine, but where do you get SSH? How do you get one? It's not so complex. You just go to some of providers on the market. You can get even access to bare metal machine or virtualized instance. Whoever heard about those two providers? Great, yeah. Probably heard about one more. So Amazon also now has ARM instances, and they run using their own chip. So they have hardware team, and they made very, very powerful chip. It's called Graviton. And you can just set up Amazon instance and run Java there. So let's check. I will show you a demo using Packet. But we'll see what works. How do you think? Will typical service work? Will it be simple? Is the screen visible? Yeah? Do you see my terminal? All right. Let's check what I have here. I have a very basic Hello World service that also contains health checks, implemented using Spring Boot. That does very simple things. Let's look at this. Oh. It is able to give me some greeting and health check. It stopped, so I can't show you a health check, but I'll show it to you a bit later. So how will I start this service? I will use Docker. No Docker Compose, no Kubernetes, no YAML files, nothing. The most powerful tool is Shell, of course, so we'll use this tool. What's here? It's base image with Alpine and Liberica, the latest security update. And I start Java from that image, where I'm able to set up this service to use only 128 megabytes for container memory. And inside this container, to achieve this, I switch only to client compiler, and I use application class data sharing. So I will use ThinkJar. Who's interested, you can check my other talk about Java and containers. And we will use Java Flight Recorder. That's available to you in OpenJDK, particularly in Liberica. And we will enable it for Java running on ARM. This is very simple. And we will start 95 such containers. Not bad, right? We also enable Jmx and everything so we could connect to this instance remotely. Just to let you see what do we have here. This is not so powerful machine, right? Only 96 cores. Whoop. But it is ARM. We'll check it again. So let's deploy this. Right? Oh. We have to wait a bit. So each of instances just gets a unique port number, like second one gets this one. It's already up and running. So what we are going to do next? We enable flight recorder there, right? Right on ARM server for a Spring application running in a container. And then we'll use Liberica Mission Control, which is a build of release Java Mission Control, Java Mission Control 7, to connect to this instance and to see what happens there. By the way, you can just go and download and use it. It's free. So here you see I already connected to this one. So we can check what Jmx Information will give us. All right, we are here. You see CPU load, you see memory information, and you can see the instruction set of this processor. So it's AR64, it's ARM. In next versions, you'll also get more information about containers to let you see what happens there, because sometimes it's really important. And we can create flight recording. Won't do it for 1 minute, but just for 5 seconds, for example. So here I go from this laptop to public cloud, where Docker is running, having Liberica JDK inside, running Spring, and I get flight recording out of there. To me, it looks very cool. Like, let me check. Oh, we've done socket IO already. Not bad. Anything else? No? So while it starts, we can see interesting effects. Yeah? Not as big as the one on the slide, but still very interesting. So it continues to start. So they are tuned to start in about 7 seconds, but we start a lot of them. So it's still starting. And if you look at Docker stats, we see all that containers. I think that's cool. So let's switch to presentation again. Oh, sorry. Let's join. And it was like this resolution. So if you have any questions or specific interest in mission control and what do we see here, please ask me a question. And some conclusions. We now have ARM service available to you as a commodity thing or just a cloud instance. Right now, you can go and check. It's very inexpensive. You can use your favorite operating system, which will work out of the box. You can have Java. You can install it easily. Like, for example, you can use your favorite package manager and install Liberica JDK. You can run other software. You can run Java software. And please use JDK 11, use the Berry Commission Control 7, latest stuff, get your security updates. And try ARM. It's very interesting. Thank you. Hey, we have time for questions. Yeah. Yeah.
So basically, did you test if this Oracle 3UK or Oracle 3UK port was slower than now?
So the question is about Oracle JDK and OpenJDK and what ports we have, for example, for Raspberry. So it is all the same port. So, but if we talk about ARM32 mode, if you talk about ARM64 mode, you now, with latest, like Java 12, you have only one port, which is AR64, which is better, I think, because no optimizations left, no important optimizations left just in one port, so everything has been compared. Yep. Hey, give me more questions. Who plans to try ARM instance, in fact? Yeah, it worth it. All right. Then thanks again.